Hello students, welcome to EPG Pathshala. I am Dr. Devrat Misra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Optical Properties 6 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So we will learn about the optical properties of an insulator, refraction phenomena in the refraction, briefings by refrigerants in the insulators and color center in the insulators. Optical properties of an insulator. Refraction. Most insulator crystals are transparent to visible light. This is so because the energy gap separating the valence band from the conduction band is quite large. The energy of the incident light photons is too small, therefore, to excite any electron from quantum states in the valence band to the higher energy states in the conduction band, and the photons are not absorbed by the crystals. When a light ray passes from air into such a crystal, its propagation direction usually is altered by a small amount. This phenomenon is called the refraction of light, and the angle of refraction r is related to the angle of incidence I according to the Snell's law, that is sin I divided by sin r is equal to n2 by n1, where n1 is the index of refraction of air and n2 is the index of refraction of the crystal. The index of refraction of vacuum is set equal to unity, and the other indices are determined accordingly. Since the index of refraction of air is 1.003, air is frequently used as the reference standard instead. Usually, some of incident light is also reflected and the angle of reflection equal to angle of incidence. Note that if the index of refraction of the crystal N2 is less than the index of surrounding medium N1, it is possible that for some value of angle of incidence, sin I is greater than 1. Since sin r cannot exceed unity, none of the light is refracted, that is, all of it must be reflected. Thus, when the index of refraction of the first medium is less than that of the second medium, then for angles of incidence greater than some critical value, total reflection occurs. The physical reason for refraction is that light travels more slowly in a dielectric medium than in vacuum. The velocity of light in a dielectric is determined by the index of refraction, V is equal to C by N, where C is the velocity of light in vacuum, which is 2.998 into 10 to the power 10 centimeter per second. Since light is a form of electromagnetic radiation, the retardation is due to the polarization of atoms in such a way that the induced electric field opposes the electric field of the incident light. It can be shown that the dielectric constant of a dielectric crystal is equal to the square of its index of refraction, so that the Clausius-Mosotty equation can be written as n square minus 1 by n square plus 2 is equal to 4 pi by 3 into summation over I ni alpha I, which is called the Lorentz equation, when n is very nearly equal to unity, so that n square plus 2 is equal to 3. Equation 2 becomes n square is equal to k E, which is equal to 1 plus 4 pi into summation over I ni alpha I. Multiplying both sides of 2 by m by d, where m is the molecular weight and d is the density, m by d into n square minus 1 by n square plus 2 is equal to 4 pi by 3 into n0 into alpha, where n0 is Avogadro's number and alpha is the polarizability of a molecule, so that equation 4 can be used to calculate the molar polarizability or the molar refractivity. This equation allows one to relate the index of refraction of a crystal to its structure. Birefringence. The index of refraction of glasses and of crystals belonging to the isometric system is independent of the direction of propagation of the light. Such crystals are said to be optically isotropic. It is important for the discussion in this section to realize that when light propagates along a certain direction, the electric field varies sinusoidally at right angles to the propagation direction. The electronics, displacements, and the resulting dipoles, therefore, are also orthogonal to the propagation direction. In tetragonal and hexagonal crystals, a light ray traveling parallel to C axis encounters an isotropic structure since A1 is A2 in these crystals. Note that this is just like a light ray traveling along A3 in a cubic crystal. A light ray traveling in a general direction, however, encounters an anisotropic structure, so that it is not surprising that it travels with a different velocity. The c-axis is therefore an optically unique axis in such crystals, and it is called the optic axis. Since there is only one unique direction in tetragonal and hexagonal crystals, they are called uniaxial crystals. In order to study the properties of anisotropic crystals, it is necessary to use plane polarized light, that is, light whose electric field is constant to alternate in a single plane containing the direction of propagation. The polarization direction is usually called the vibration direction of the light. When a ray of plane polarized light traverses a uniaxial crystal parallel to the optic axis, then regardless of the vibration direction of the electric field, the index of refraction is the same and is usually denoted omega. When a ray traverses the crystal along a direction which is normal to the optic axis, then the index is as before omega. When the vibration direction is parallel to the optic axis, the index of refraction is different and is called epsilon. When the vibration direction lies between these two directions, then the light ray is split into two components whose electric field are constrained to vibrate in directions respectively parallel and normal to the optic axis, as shown in figure 2. The component parallel to the optic axis has a vibrational amplitude sin phi, and its propagation velocity is determined by epsilon, while the amplitude of the order components is epsilon cos phi and its velocity is determined by omega. The two indices of refraction, epsilon and omega, therefore are called the principal indices of refraction of a uniaxial crystal. If epsilon is greater than omega, the crystal is said to be positive uniaxial, and if epsilon is less than omega, the crystal is said to be negative uniaxial. Returning to figure 2, it is clear that since the velocities of propagation of the two components are different, the two components emerge from the crystal with a relative phase difference whose magnitude depends not only on the relative propagation velocities, that is indices of refraction, but also on the thickness of the crystal. Suppose that the thickness of the crystal is such that one component is exactly one half wavelength behind the other components, that is, they differ in phase by 180 degree. Then the emerging light has two electric field components directed as shown in figure 3, and the resultant electric field is rotated by an amount 2 phi from its original direction shown in figure 2. The phase of the component whose vibration direction is parallel to the optic axis is equal to 2 pi nu t by Ve, where nu is the frequency of the incident light, t is the thickness of the crystal, and V is its propagation velocity. Similarly, the phase of the other component is 2 pi nu t into V omega. The difference in phase delta therefore is delta is equal to 2 pi nu t by Ve minus 2 pi nu t divided by V omega, from where we can get delta is equal to 2 pi t by lambda into epsilon minus omega. Since C by nu is the wavelength of light in vacuum, Relation 5 can be used to determine the thickness of a so-called half-wave plate by setting it to be pi. Note that the relative phase depends on the frequency of the light. Suppose that the incident light ray is neither parallel nor normal to the optic axis. For example, consider light incident at point A in a direction which is normal to one of the natural cleavage faces of a calcite rhombohedron as shown in figure 4. The incident light ray is observed to split off into rays. This phenomenon is called double refraction. One ray, designated the O ray in figure 4, traverses the crystal without refraction according to Snell's law for normal incidence. When I is equal to 0, sin I is equal to 0 and sin R is equal to 0. The other ray is refracted, however, and violates Snell's law. For this reason, it is called the extraordinary ray E to distinguish it from the ordinary ray O. Regardless of the vibration direction of incident light, the extraordinary ray is constrained to vibrate in a plane containing the optic axis and the incident light. The extraordinary ray is constrained to vibrate in a plane containing the optic axis and the incident plane is called the principal plane, shaded plane shown in figure 4. The ordinary ray, on the other hand, is constrained to vibrate in a direction at right angles to the principal plane. The relative velocities of the two rays are determined by the two principal indices of refraction, and the difference between these indices is used to measure the birefringence of a crystal. Calcite CaCO3 is a negative uniaxial crystal. For the D line of the sodium, lambda is equal to 5893 angstrom, epsilon is equal to 1.486 and omega is equal to 1.658, whose relatively large birefringence can be easily understood when its crystal structure is considered. The structure of calcite resembles that of a sodium chloride cube tipped so that its 111 direction is parallel to the c-axis of the calcite. Note that the CO3 groups from triangles whose planes are oriented normal to the c-axis, which is parallel to the optic axis of the crystal. The large difference between the indices of refraction for light vibrating parallel to and light vibrating normal to the optic axis is due to this orientation of the carbonates group. Consider a carbonates group consisting of 3 oxygen atoms lying at the corners of an equilateral triangle and the carbon atom at its center, as shown in figure 6. When the vibration direction of the electric field is normal to the plane of the triangle, the oxygen atoms are polarized so that the induced dipoles are also normal to the plane of the triangle. Their direction is such that it opposes the direction of the external field. Figure 5 shows the crystal structure of CaCO3 compared with that of sodium chloride. Only the calcium atoms and CO3 groups situated on the front faces of the calcite rhombohedron are shown. The carbon atoms are hidden from sight by a much larger oxygen atoms. Each dipole, therefore, tends to depolarize its neighboring oxygen dipoles. When the vibration direction of the field is parallel to the plane of the triangle, then two of the induced dipoles tend to reinforce the third, and simultaneously the third dipole tends to reinforce the other two. This can be seen from the induced field directions indicated by small arrow in figure 6b. Although the fields in two adjacent oxygen atoms oppose each other, it can be shown that the average increase in the induced electric field intensity exceeds the average depolarizing field intensity. Accordingly, a light ray vibrating in the plane of CO3 group in calcite is retarded more than a light ray vibrating in a direction normal to the plane. Since the optic axis of calcite is normal to the plane of the CO3 groups, and since the index of refraction is inversely proportional to the propagation velocity, a calcite which is less than omega, and calcite is optically negative. Crystals belonging to the orthorhombic, monoclinic and triclinic systems have two optic axes and are called biaxial crystals. There are three mutually perpendicular vibration directions and three indices of refraction called alpha, beta and gamma. These directions of vibrations bear definite relations to the crystallographic symmetry of a biaxial crystal, and the magnitudes of the indices of refraction are intimately related to its structure. As expected from their structures, the birefringence of quartz is much smaller than that of the more anisotropic structure of hornblende and muscovite. Note that the birefringence of biaxial crystals is determined by the numerical difference between the largest and the smallest index. It should be obvious from the above discussion that the optical properties of crystals are strongly structure sensitive. In fact, it turns out that the refractive index of all transparent crystals are as unique as fingerprints. This immediately suggests that refractive index determination can be used as a routine analytical tool for identifying such crystals. Mineralogists realized that this long before the physical cause of the refraction of light were fully understood and have complicated extensive reference tables for just this purpose. In this connection, it should be noted that X-ray diffraction diagram of crystals are also related to crystal structure and can be used in an analogous way for identification purposes. Moreover, X-ray diffraction has the advantage that the crystals need not be transparent. Both methods of analysis, nevertheless, are in widespread use today. Color centers. As already noted, most insulator crystals are transparent to visible light. Occasionally, however, these crystals appear to be colored. It is believed that the color of a crystal is due to the selective absorption of some component of the visible spectrum by certain imperfections called color centers, which are present in the crystal. These imperfections may be interstitial impurity atoms such as transition metal ions. Alternatively, there may be vacancies in the structure produced by deviations from stoichiometry, so that there are present excess positive ions accompanied by negative vacancies, or excess negative ions accompanied by positive vacancies. Thus, when excess zinc is present in ZNO, it takes on a yellow color, whereas excess lithium in LiF turns the crystal pink, and excess potassium in KCl makes the crystal appear violet. When an alkali halide crystal is heated in an atmosphere containing an excess of the alkali metal vapor, the excess metal atom deposit on the crystal surface. Halogen ions then may diffuse to the surface, where they combine with the metal atoms which have become ionized by losing a valence electron. This electron in turn can diffuse into the crystal until it encounters a negative ion vacancy with which it combines. A similar end result is obtained when an excess of the alkali metal is incorporated in the crystal during its growth. The quantum state of such a trapped electron lies somewhere in the forbidden energy region. The exact energy value of this state depends only on the environment of the vacancy, that is, the crystal structure, and not on the metal atom from which the electron originally came. It does not matter, therefore, whether the excess metal present in the crystal is the same as the metal normally present in the host crystal, or not. When the crystal is irradiated with white light, some components of this light has the appropriate energy to excite the trapped electron to a higher lying quantum state, so that it becomes absorbed by the crystal in the process. Although the process of absorption by these so-called F centers is only approximately understood, it is believed that the electron is excited to another quantum state also lying in the forbidden region. Actually, a range of energies can excite this electron that an absorption band called the F band is observed. It has been shown that the total absorption is directly proportional to the number of excess metal atoms in the crystal, that is, the number of F centers produced. The F absorption band is not symmetrical about a central energy value, but has a tail on the short wavelength side. This tail is believed to be due to electronic transitions to quantum states having higher energies, but still lying below the bottom of the conduction band. The name K band has been proposed for this section of the absorption band spectrum. As might be expected, the excited electrons should be able to contribute to electrical conductivity, since they now occupy quantum states close to the bottom of the conduction band. Photocurrents are indeed observed. However, it is necessary that electrons flowing to the positive electrode be replaced by other electrons injected into the crystal by the negative electrode, so that space charge do not build up inside the crystal. Alternatively, in the absence of an external electric field, it is reasonable to expect that the excited electrons can return to their ground states by the emission of a photon of light. Luminescence is actually observed in additively colored alkali halides. However, it is necessary to maintain the crystals at low temperatures so that the electrons are not thermally excited to quantum states in the conduction band. It is possible to produce halide crystals containing excess halogen ions. Such excess ions are accompanied by positive ion vacancies, which serve to trap holes quite similarly to the way the anion vacancies trapped by the electrons. In order to distinguish the color centers thus produced, they are called V centers. It turns out that the absorption spectra of crystals containing V centers show several absorption maxima, so that there is apparently more than one kind of transition possible. These absorption maxima are usually designated V1 bands, V2 bands, etc. A curious effect is observed when a crystal already containing F centers is irradiated at elevated temperatures by light that is absorbed by these F centers. The absorption of the F band is gradually decreased following such an irradiation. This process is called bleaching, and a new absorption band lying on the long wavelength side of the F band appears. This new band is called the F band, and it is believed to be produced in the following way. Some electrons that are excited by the incident light become free electrons by absorbing thermal energy. These electrons subsequently can combine with other F centers. This produces an F center which is believed to be an F centers that containing two electrons. As expected from this model, when a crystal containing F centers is irradiated by light that is absorbed by these centers, F centers are produced in turn. Since the energy of this light is less than that necessary to excite electrons trapped in F centers, the reversible effects described above are consistent with energy band model proposed to explain them. It is possible to produce color centers in still another way. When a crystal is irradiated with high energy radiation in the form of X-rays, gamma rays or neutrons, color centers are also produced. The process in this case first consists of the production of recoil electrons by the incident radiation, followed by the interaction of these electrons with the valence electrons to produce electron-hole pairs. Consequently, such irradiated crystals usually contain both F and V centers. Unlike the stoichiometrically deficient crystals, however, the crystals that are colored by radiation can be easily bleached by re-radiating the crystal with visible light or by annealing them. This is so because the excited electrons and holes ultimately recombine with each other. So students, let us summarize what we have learned in this module. Optical properties of an insulator are explained. Birefringence are also explained and its temperature dependence is also described. Color centers and its various types are also explained. Thank you.